Okay, all right. So here's where we were last time. We just barely started talking about linear algebra. Specifically, we're defining something called a linear transformation. It turns out this is a very important object in linear algebra. Defining a special case of linear transformations here in this section, just so you know. Some of y'all will be taking Math 216 in the fall, or Math 221, some sort of a linear algebra course. We're only going to define linear transformations on Rn and Rm. Right, so this is what we call Euclidean linear transformations. There's a more general construction that's morally equivalent to this, but nevertheless more general. So it's defined by these two properties. These are two properties that some functions satisfy. Most functions don't. Right? Easy to find examples of functions that don't do this. So for example, the squaring function. If you square a sum of two numbers, you do not get the sum of the individual squares. Right? So again, most functions don't have this property. Sometimes adding inputs is this equivalent to adding outputs. Multiplying an input by a scalar effectively multiplies the output by a scalar. Sometimes functions have these two really convenient properties. Okay, so if these two properties are satisfied, we say we have a linear transformation, and it turns out we can do really powerful things with linear transformations. Take Math 216 or Math 221 or Math 218 if you want to see more about that. Okay. All right, now it turns out that these two conditions are equivalent to this one condition. So the way I like to say it, by the way, this condition says that the function plays nice with vector addition. Plays nice in the sense that you can do the vector addition before you plug into the function. You can do the vector addition after you've plugged into the function, and it kind of goes either way, right? Sometimes we say commutes with vector addition. Okay. Well, here's the thing. If a function plays nice with vector addition and plays nice with scalar multiplication, notice that all this says is that the function plays nice with linear combinations. And what are linear combinations? Linear combinations are just, addition and scalar multiplication. Right? So I think it should come as no surprise that addition and scalar multiplication properties combine to give you a linear combination property, and vice versa. Okay, pretty believable. Further true, this statement about linear combinations, notice this is a statement about linear combinations of a pair of vectors. Right? Well, as it happens, it does not have to be just a pair of vectors. You can talk about linear combinations of any number, any finite number of vectors. So it is equally, that was a bad choice of adverb. It is equivalent to say that a linear transformation plays nice with arbitrary linear combinations. Okay, all right. Alrighty. So here's what this looks like geometrically. Let's look at linear combinations of a pair of vectors. Here I have a couple of input vectors. And here I have a linear combination of those input vectors. Now remember, what is a linear combination? A linear combination says I'm going to take a scalar multiple of one vector. I'm going to take a different scalar multiple, presumably, of the second vector, and I'm going to add those. That's what a linear combination is. So roughly speaking, a linear combination is something that you can make you can make a parallelogram whose edges are parallel to the two input vectors, if you want to think about it that way. Okay. These two input vectors, I can look at their outputs by this linear transformation. Inputs have outputs. Right? And I could take the same linear combination of those two output vectors. So same multiple of that first vector. What is this? About 1.5 times the first vector. Okay, so take 1.5 times this first output vector. Likewise, take about half or so. About half then of the second output vector. And if you take that linear combination The idea is that the input linear combination has as its image the output linear combination. So geometrically, this is kind of the picture that linearity, that this formula, or this property right here, what that property looks like geometrically is this, and it kind of, I don't know, it sort of suggests that roughly speaking, as long as parallelograms going in go to parallelograms coming out in some sense, right? So you can rotate things around, maybe kind of shift, stretch, these kinds of certain things that you can do as long as this input parallelogram picture in the output always has a corresponding output parallelogram picture. That'd be one way to think about linear transformations. Okay, now let's get our hands dirty and actually show directly, brute force. Sometimes you have to do this. Brute force demonstrate that a function is a linear transformation. It is very, very far from obvious, but I claim that this function right here is a linear transformation. And we're going to prove this directly from the definition. I'm going to, this is going to be a certain amount of tedium, but I'm going to put a linear combination into that function, and by compute, I'm going to show that we get the corresponding linear combination out of the function. So linear combination goes into the function, linear combination, same linear combination, comes out of the function. Everybody see that what we're trying to do here? Brute force, here we go. So we're going to start off by saying, all right, look, this x has certain coordinates. This y has certain coordinates. Let's write those out. Right, here's the x vector. Here's the y vector. I didn't really do anything. I'm just plugging in for what the coordinates are. Sort of expanding by coordinates. I can multiply out this input vector. Right, I've got all the coordinates. I know how to multiply vectors by scalars. I know how to add vectors. And multiplying out that input vector, again, I haven't really done anything. I'm just sort of simplifying what is actually going into this function. All right, now, notice what we have here. What we have is, let's evaluate this function f. We have a formula for how to evaluate this function f. The thing that's going into this function f, the first coordinate of the input, is this thing, ax1 plus by1. I don't think I highlighted that right. Here we go. And so that first coordinate is going to go there and there. And then the second coordinate of this input, the thing that is kind of the x2, if you will, in this general formula, is going to go there and there and there. And that makes this expression turn into this. I just got in my own way. Okay, so 2x1 plus x2, x1 minus 3x2, and then 5x2. You can see all I did here is I plugged in to the function f. I kind of still haven't really done anything. I'm just computing what I've been given to start with. Computing that input. Okay. All right. Now, this resulting all this business over here. Now let's cheat a little bit. I look ahead. I know I kind of need all the A's sort of on one side, and I also need the X's and the A's kind of all on that one side. I need all the Y's and the B's over to the right hand side. So I'm just going to take the terms in here that have X's and A's in them, and I'm going to kind of just sort of clump them all over here. You'll notice also simultaneously factoring out the common factor of A. Right? And then I'm going to take all the terms that have Y's and B's in them. So this and that and that and that and all the terms with Y's and B's, I'm going to sort of group them over here. Again, factoring out that common factor of B. So, just rearranging. And the result is, having rearranged terms in this way, notice, direct observation, this is f of x, and this is f of y. And so there it is, sure enough, right? As required, linear combination of inputs yields linear combination of outputs. So, check. So, brute force calculation, we've confirmed that this is a linear transformation as we wanted. Okay, all right. So I hope you're unimpressed, right? There's nothing, there's no slick moves in there. This is just plug and chug directly confirming that the function satisfies the rule. Okay. All right. Now, that's nice. Let me remind you though, very importantly, not all functions are linear transformations. In fact, most functions are not linear transformations. It's all too easy in a class where we're going to do a bunch of stuff with linear transformations to just kind of get accustomed to taking advantage of linearity and just thinking everything's a linear transformation, when it's not. That the old saying that if you spend a lot of time working with a hammer, everything you see looks like a nail. That happens as well. So let me just combat that. Here's a direct observation. Here is a function that is not a linear transformation. And we're going to directly show it's not a linear transformation. Now, there's a temptation to say, oh yeah, because look, something's squared. And yeah, kind of, that's a good intuition for suspecting that this probably is not a linear transformation. But if you want to show that something is not a linear transformation, you have to explicitly demonstrate that it does not satisfy the required property. And the way I'm going to show it does not satisfy the required properties, I'm going to find a counterexample. If this were a linear transformation, these two things would have to be equal. Well, plug in. Not too much trouble to plug in. Plug in 2, 0 into that function g, and out comes 12, 0. Plug in 1, 0, and then do the appropriate linear combination here. And out comes 6, 0. And notice that these two things, they're supposed to be equal, are not equal, and therefore this is not a linear transformation. How are we doing? Everybody on board? Okay. Most of the time. Most functions, not linear transformations. Okay, there's a few sort of foundational facts about linear transformations that we have to establish. The first one's a nice little quickie. It turns out if you have any linear transformation at all, any linear transformation, the image of 0 is 0. Isn't that nice? It turns out it's a really easy property to prove. Let's consider, just because we feel like it, what is t of 0 times x? Here, let me zoom for focus. What is t of 0 times x? Well, this being as it is a scalar, factors out, and so my result must be 0 times t of x. Well, the thing is, that is definitely the 0 vector. Doesn't even matter what x is. Right? And this, being as it is the 0 vector, that is equal to that. So the fact that this is an immediate consequence of the linearity condition, that implies that this equation is always true. So, like I say, real quickie, smart alecky kind of proof. I like those. Okay. All right. Here is another neat fact about linear transformations. Quick recall. Standard basis vectors. I hope you all remember we talked about standard basis vectors back in chapter 1. These are the standard basis vectors for R3, for example. So standard basis vectors are just they're the unit vectors pointing along axes. Right, so their coordinates are mostly zeros with a single 1 in the appropriate position. Okay. Notice the pattern with the subscripts. E1 has the 1 in the first position. E2 has the 1 in the second position. E3 has it in the third position. Okay. All right, so that having been observed, here's a really surprising and important property about linear transformations. If you know the images of the standard basis vectors, let's just say we've got some linear transformation. If you know the images of the standard basis vectors, then you know every other value of the linear transformation. It's like a magic trick, right? So, there's here, you think of a linear transformation that's defined on all of the infinitely many vectors of R3, let's say. This is your linear transformation. You think about it. Don't tell me what it is. Right? And then I'm going to ask you to tell me what's T of E1, what's T of E2, what's T of E3, and then I'll tell you exactly what your linear transformation is. Presto. Right? It's kind of like a magic trick. So the reason that this works, I'm going to show you the proof momentarily, but morally speaking, the reason that this works is because the vast majority of functions are not linear. There are very, very few linear transformations. There are so few linear transformations that only one of them could possibly have the values on the standard basis vectors that you tell me. It's kind of why the proof works. So anyway, here's the proof. I'm supposed to tell you t, value of t, for some vector x. All right, well, let's suppose that vector x has coordinates x1 through xn. Here's the way I'm going to compute what you wanted. We want to compute t of x. There's how I'm going to compute t of x. Keep in mind, if these are the coordinates, right, then those are the coefficients in a linear combination that makes up the vector x itself. Right. Then, good news, this is a linear transformation. Because it's a linear transformation, linear combination in gives me linear combination out. And the images of the standard basis vectors, t of E1 through t of En, are all known. Right? So I know what these are. So that means that if you give me some vector x, and therefore if I know all the x1s through xn's, then I know everything that there is, all of the stuff that it needs to go into this calculation of t of x. I know everything inside that blue circle. So I can totally compute t of x. This is straight up. We say we compute it by linearity. We use the linearity to relate t of the input combination to just, t of the output combination, which I already know. Okay. All right, that ends up being a really big deal. Okay, here's, again, kind of a picture of that proof. You'll notice that this picture looks an awful lot like this picture. We got parallelograms on both sides. Right? That's what linear transformations do, is they kind of turn parallelograms into corresponding parallelograms. So this is morally kind of the same picture again, with a little bit different, in the sense that, suppose that I know, let's see here, suppose that I know the images of E1 and E2. Okay, so suppose I know T of E1 and T of E2. That's the premise. Then, if you give me some combination of E1 and E2, that means I know what these coordinates are. Right? By linearity, I know that the output, what that's going to go to, I know that output is the same linear combination of these two images that I'm told, that I know. And then just by taking the appropriate linear combination, using linearity, I get that output. Now, so again, it's slightly different context, but it's morally the same idea. So another way to say this is that that really this fact and this proof are just restatements of linearity. Okay. All right. Okie dokie. So, all right. Now, what do these things look like? How do you think about linear transformations? The following is not terribly hard to prove, but I don't want to go through the proof. It takes a little bit of time, and we just don't really have the time. But it's good to have an intuition for what linear transformations kind of look like. And the way I like to say this is, linear transformations deform the domain in a uniform way. I mean, I'm going to use the term linear here, but that's a little bit circular. A uniform way. Ultimately, what is in fact linear. So here's what I mean by deform the domain. Here's our domain, and notice that what this function has done is it's picked up the domain and it's done some stuff to it. It's deformed it. Right now, it's all kind of rotated and bent in some way. Right? So that deformation is, I'm going to say uniform in the sense that how stuff over here gets deformed is the same as how stuff over here gets deformed, which is the same as how stuff over here gets deformed. So a couple of examples of what we're talking about. Lines that are parallel in the domain. Their image lines, their image lines are going to be parallel in the target. So the way things get kind of bent around over in this side and the way things get bent around over there, it's the same kind of bending. They both get angled kind of by the same amount in some sense. There's a uniformity. Likewise, if you were to, let's see here, I'm going to use a pencil. If you were to look at a little square right there, right, and you look at its image, the image of that little square is, oh gosh, it's going to be something kind of like that, right? So what's happened to the stuff that was inside of our original square? Well, it appears that it's been kind of rotated counterclockwise, and then it's maybe been stretched sideways, and then maybe squished height-wise. You can see what I'm talking about, right? Well, way over here, that little region gets bent around. Let's see if I can artistic challenge here. Gets bent around in an analogous way. And you can see that the idea is that these two things that have the same shape in the domain, their images have the same shape in the target. Okay, so this is the uniformity that I'm talking about when I say that the domain gets deformed in a uniform way. That's what we're talking about. So linear transformations are ultimately very sort of organized. They're very methodical, you might say, kinds of functions. And it's good to have some intuitive sense of what's going on geometrically. Okay. Alrighty, some examples. Let's suppose that I have a linear transformation from R2 to R3. Okay, so here's our domain, R2. Here's our target, R3. And let's ask and I know a couple of inputs. I know that E1 has as its image 1, 2, 1. Right, and I've used these dotted lines to try to, just for sort of scale purposes, to make that look like you can see that that's 1, 2, 1. Okay. And suppose I also know that E2 has as its image -1, -1, 3, which again, with the dotted lines, I'm using that vector to represent -1, -1, 3. Okay, so those two images are given. Well, check it out. I know the images of the two standard basis vectors in the domain. Therefore, everything else, all the other images of this function, they're all going to be determined by linear combinations. So, since everything in this plane is some sort of linear combination of E1 and E2, right? All of their images, and therefore the image of the entire transformation, are going to be, well, corresponding linear combinations of those two output vectors. So the image of the entire linear transformation is that plane that's defined by those two image vectors that are given. Everybody on board? Just, for example, just one sort of geometric example. Okay. Let you all read this example on your own. There are many functions that we've looked at in the past, and some of them are linear transformations, some of them aren't. Stretches are linear transformations. Reflections are linear transformations. And translations, though, are not. So you can think about why those statements are true, but I'm going to let y'all mostly read that. I want to move on to this example about rotation. Here's a function. Now, I claim that this is a linear transformation. You can just directly plug into the condition. Linear combinations in, chug, chug, chug. Confirm you get linear combinations out. It satisfies the formula. It's a matter of brute forcing it. So that's a linear transformation. Turns out we can find a formula for what this does. Not hard to confirm that the first vector has as its image that. The second standard basis vector has as its image that. So if I'm interested in some linear combination of E1 and E2, well, then the same linear combination of the images is the output value. Right? Okay. So now let's look at this picture and think about what this picture has done. This function, let's look at what it did to E1. E1 got rotated counterclockwise by pi over 2. E2, right, started off vertical, started off over here, and then it rotated around. It has rotated counterclockwise by pi over 2. And this suggests, that rotates the exact same rotation for both of those input vectors. Let's think about when you take these two vectors here, when you rotate 90 degrees, I appeal to your geometric intuition. Any parallelogram based off of these two vectors would just kind of rotate right along with it. Right? So this kind of suggests, maybe makes us wonder, could it be that this vector, this arbitrary input vector, maybe it just rotates by pi over 2 as well? And in fact, that's true. So this function right here, this is a rotation by pi over 2 counterclockwise around the origin. This simple function will take any vector at all, and will rotate it 90 degrees counterclockwise around the origin. Okay. By the way, this is easily confirmed because you can just directly confirm that the input vector and the result of that function, that dot product is always 0, and that means they're orthogonal, and that means that one's a rotation of the other. So, easy to confirm. Okay. I'm going to assert that rotations in general are linear transformations. I do want to draw a picture of this where I have some space. So I've got some space over here. Color-wise. Rotations are linear transformations. The way I'm going to demonstrate this is by drawing a parallelogram that represents a linear combination. So this is a linear combination of those two green vectors. And now I'm just going to take this entire parallelogram. I'm going to rotate the entire parallelogram around the origin by some arbitrary angle. Right? The whole parallelogram. I wish that my little markup app would do this for me, but I'm going to have to eyeball this. So forgive me for the imperfection on this. Okay, and then so there I've rotated the entire parallelogram pretty decently, if I do say so myself. So I have a parallelogram and its rotation. So let's just think through now, what do I conclude from this? Well, everything on the orange parallelogram has rotated into the purple parallelogram, and what that tells me is if I take these input vectors, if I rotate them first, and then do the linear combination, right? That's the same as, just again, look at the parallelograms. That's the same as taking the original vectors, doing the linear combination, and then rotating. Right? So that's just how rotations work. Rotations turn a parallelogram into another parallelogram, and just drawing the picture and thinking it through, that means that rotations are linear transformations. Okay, having observed that powerful observation, once we know that rotations are linear transformations, I can understand then the entire rotation, a general rotation by any arbitrary amount, as a function simply by understanding what is the rotation of the first standard basis vector and what's the rotation of the second standard basis vector. Right? If you know what a linear transformation does to the standard basis vectors, everything else is just a linearity argument. So these are pretty easy to identify, as it turns out. If you want to rotate the standard basis vectors, no problem. Right? Here's E1, rotate by an angle theta. Think back to high school trig class. This vector, if that angle is theta, this magnitude was 1, therefore that magnitude is 1. It's cosine comma sine. Right? So cosine theta, sine theta. Likewise, what is the rotation of the second standard basis vector? Well, okay, I mean, it's a little bit different of trig, but nevertheless, there's our second standard basis vector. Rotate it by an angle theta. Again, flashbacks to trig. If you're maybe a little shaky on how to do this, be a good thing to brush up on. Now, again, trig does not go away. We're going to be using and assuming a lot of trig in this course. And the coordinates of this vector are negative sine theta, comma cosine theta. There you go. And once you know the images of the standard basis vectors, I just erased. Once you know the images of the standard basis vectors, everything else can be determined by linearity. Right? And just kind of multiply that out, and you get this formula. And so here's a magic formula. It's starting to get pretty non-trivial geometrically. Give me any arbitrary vector, however weird, in R2. You want to rotate by any angle theta, however non-standard. This doesn't have to be, pi over 6, pi over 4. This could be, 34.7 degrees. And this nice little formula here, compact little formula, will tell you what happens when you rotate that arbitrary vector by that arbitrary angle. This is a powerful result. And try that without linear transformations, and it's hard. It's very hard to do this with just straight up high school trig. Okay. There's a couple more examples in there. I'm going to let y'all read those. Moving on now to matrices. Some of y'all have probably seen matrices before. Just out of my own curiosity, how many people know how to multiply matrices? Very few. Okay, but a few of you do. Great. Okay. What is almost never presented in high school, classes that talk about matrices, they'll usually talk about how to multiply matrices. But what's rarely presented is an argument for why that weirdo formula is the choice. Why do we do that formula for matrix multiplication? I have yet to meet a student who had a really confident, strong understanding of why that is. So I'm going to show y'all, and I think this is valuable. I mean, ultimately, your high schools didn't have the ability. It would presume that you knew some more linear algebra than would be feasible to talk about in a typical, pre-calculus class. But what it really takes understanding of is linear transformations, and we now have seen linear transformations, and so here we go. Okay, let's look at that linear transformation right there. We've already shown that's a linear transformation. That's the one we showed brute force a little while ago. Okay. I claim that what I have circled here in the second circle, this information tells you all of the information that the formula does. This tells you how to compute the linear transformation for any x1, x2. But what is this? this tells you the images of the standard basis vectors and notes that we have a linear transformation. And we proved in the last section that that allows you to compute the linear transformation for all possible x's, just like this does. Okay. So we're going to capitalize on this with a notation. The notation is that of a matrix. This matrix going forward will be a shorthand to represent this, which, as we've already seen, represents that. And the idea is as follows. The convention, when you see a matrix, the convention is the columns are the images of the standard basis vectors. And matrices are always understood, any matrix, always understood to be representing a linear transformation. And, well, if you know you've got a linear transformation, and if you know the columns, if you know the images of the standard basis vectors, well, then you know the linear transformation. Okay, so what we have then is, by those assumptions, this is a very compact and convenient shorthand to represent that slightly clunkier, fully, fleshed out linear transformation. All right, everybody happy? Okay. Matrices get defined in different ways in different books, in different classes, different contexts. There are different definitions of matrices. This is the one that's going to be the most useful for what we're doing here. Okay, yeah?
Sorry, is there a reason we use parentheses versus brackets?
Oh, it doesn't matter. Yeah, some people like to use brackets. It doesn't matter. Yeah, right. Yep, great question. Yeah. Okay. All right, so here we go then. Yeah, so that's the definition. Definition of a matrix. A matrix representing a linear transformation. In this class, we're defining it as it's a matrix where the columns are the images of the standard basis vectors. Okay. All righty. A couple of quickie examples then. Here's a linear transformation. How would I represent this with a matrix? Well, there's 3 input vectors. That means my domain is R3. There are therefore 3 standard basis vectors. I can directly plug in and I find these are the images of those 3 standard basis vectors. That's just plugging straight in. Plug in E1, plug in E2, plug in E3. And note that those are simply the columns then. And that's my matrix representing that linear transformation. Okay, let's turn it around. Suppose somebody gives you a matrix and then says, reverse engineer for me, what was the linear transformation that this represents? Okay, well, this matrix, what linear transformation is this shorthanding? Well, I know that the columns are the images of the standard basis vectors. Again, that's the definition that we're using of a matrix representing a linear transformation. So if you know the images of the standard basis vectors, then again, by linearity, for any vector x with coordinates x, y, and z, just multiply it out, and there's your formula for t of x. So, give me a linear transformation, we can make a matrix. Give me a matrix, we can find the linear transformation. These things are sort of corresponding at this point. Okay. All right, so with this point of view, I claim we're going to be able to answer a lot of questions. Let me go back real quick to this. Yeah, I'll do it here. We've got this idea of linear transformations. Matrices are just their shorthands. Now I'm going to start considering questions that some of y'all, those of you who have seen some matrix algebra before, have seen. You've seen the whats but not the whys, and the answer to the whys are always going to take a certain form. How should I do a certain operation with matrices? Answer: don't forget they just represent linear transformations. If you want to know what a matrix does, what does the linear transformation do? That's what the matrix does. After all, the matrix is just a way to represent the linear transformation. So, Let me show you an example of this sort of strategy in action. Let's ask, how should we multiply a matrix times a vector? What should it mean to multiply a matrix times a vector? And I know, again, a lot of y'all have probably seen that formula. Again, show of hands, curiosity, matrix times a vector. Some, again, not many. Okay, fine. No problem. If you haven't seen this before, arguably a good thing. Okay, so we ask the question, what should this mean? Answer, well, this matrix is just a way of representing the linear transformation. So matrix times vector. What a matrix does to a vector really ought to be the same as, well, what does the linear transformation do to that vector? Right? I mean, they're supposed to be kind of the same thing in the sense that one represents the other. So, so the choice that I'm going to make for this is going to be a direct computation of, what would this have been? Okay, so that's the strategy, and now let's see how those details work out. In order to do this, I need to be able to talk about certain aspects of the matrix. Specifically, I want to be able to talk about the columns of the matrix, so I'm going to use this convention. I'm going to use A1 through AN, lowercase A1 through AN, to represent the columns of this. If you give me an arbitrary matrix A, it's convenient for me to be able to label the columns. So there we go. Given some vector X, that vector X, again, I need to be able to refer to what makes it up. So I'm going to give names X1 through Xn to its coordinates. It's just notation. Having set that all up, and having decided that this product that I would like to define had better equal to this, here we go. It turns out that we kind of don't really have any choice in the matter. In fact, everything's going to fall in our lap. What is AX? Well, it had better be T of X. By linearity, T of X is this. Right? That's what linearity says. And what are the images of the standard basis vectors? Well, the images of the standard basis vectors are the columns of the matrix. That's the definition of a matrix. The columns are the images of the standard basis vectors. This T of En is the nth column, AN. And so here's our formula. By the way, if you have seen matrix vector multiplication before, you might notice that this is not what you have seen before. I'll get to that. The formula you've seen before it's not wrong. It's just that's not where I'm going with this right at the moment. We'll get to that momentarily. But anyway, here's our answer. If you want to multiply a matrix times a vector, that matrix is made up of columns. You can see here we are taking a linear combination of those columns. The coefficients in that linear combination are just the coordinates of the vector x that you're multiplying by. So there you go. Matrix vector multiplication, matrix times vector, linear combination of the columns of the matrix, coordinates of the vector as coefficients in that linear combination. And that's the definition that I have written down here. This formula right here is that definition. How are we doing? Does everybody understand the reasoning there? I mean, I'm painted into this corner. I kind of don't even have a choice. Right? Arguably, the only choice that I made here was, well, I would like for matrices to act in ways that correspond to what they represent. I mean, that's the one choice. Everything else is dictated to me by linearity and definitions. Okay, so I think that's pretty natural. And if you have seen matrix vector multiplication before, again, it was pretty arbitrary that, we're just going to do a certain formula. Why? Oh, no, it just is. This is the definition and no explanation given. I think this is very satisfying. This definition is what it is because of what matrices ultimately represent. Okay, all right. Okay, now what about that formula that you've seen before? Here's the formula that you've seen before. The formula that most of you have seen before is that if you want to multiply a matrix times a vector, then you look at the rows of the matrix, and then you do dot products of rows dot, well, that one vector. Right. So I think this is the more common formula used in high schools, and pros and cons. Now, how is it that these two are the same? I mean, that doesn't at a glance look to be the same as that. One involves the columns, one involves the rows. How could these be the same? Right. Okay. Well, it turns out they're exactly the same. Here's the way you can see that. This linear combination here going to have certain coordinates. If you were to, keep in mind what we're taking linear combinations of, these vectors A1 through AN, those vectors are, well, they're vectors. So a linear combination of them is a vector. Let's ask now momentarily, where does the first element of that vector, that product vector, come from? In this linear combinations formula, how would I compute that first element? And I'm taking linear combinations of a bunch of vectors. When you add vectors, you do it coordinate-wise. When you scalar multiply vectors, you do it coordinate-wise. So this first vector is going to be sort of the appropriate linear combination then of the first coordinates of the A vector. Of the column vectors. Okay. So we're going to be taking then the x1 through xn linear combination of those first entries in each column. Said differently, we're going to be taking this linear combination of those first entries in all of the columns. Think about what a linear combination of numbers is. In fact, it's just a dot product. You can see the arithmetic right there. Multiplying these as coefficients times these as numbers is the dot product that we have defining that right there in this other point of view. So again, at a glance, they don't look the same, but they really are entirely equivalent as definitions. All right. Now, here's a common complaint students make at this time, and they say, well, look, computationally, this is really convenient because I can just see that row right there, and I can see this column right there, and it's like I can do the dot product in my head. This dot product, I'll just write it down. Right? Whereas if I want to do this linear combinations formula, I kind of have to write the whole thing down, and it just takes up more space. It uses more pencil lead. So why would we ever do this when we could instead do this? Pretty tempting, right? Let's see an example. I'm going to compute this matrix vector product two different ways. First, let's do it the new way, the way that you probably did not see in high school. Here's the linear combinations formula. We take these columns. Here they are. There are those columns. We're going to do a linear combination with these numbers as our coefficients. Again, that's our new point of view on matrix vector products. And you multiply that whole thing out, and you get that as the result. Well, now let's do it again. This time, what I'll call the easy high school way, if you will. Right? And okay, well, here are these rows, each of which is dotting with this column, same column. And you can do those dot products out, and there you go, and you get the same answer. So, I mean, what's the difference? Why not do it the way that's easier? And I do have a good answer for this question. It's not something that you can immediately sink your teeth into, but I'm going to start by confessing that if it comes down to actual arithmetic, when it comes down to arithmetic, oh yeah, 100%, for sure, do it this way. It is easier for arithmetic. And what you have to keep in mind, though, is that's not going to be most of what we're doing in this class. Most of what we're doing in this class, most of what we're going to be doing in future classes is relating ideas to other ideas. Reasoning, right? Trying to understand why certain formulas work the way they do, this kind of thing, right? And it turns out, again, you can't see any of this coming necessarily right away, but understanding how matrix vector multiplications are linear combinations ends up being really valuable. And this is going to allow us to draw connections. This is going to allow us to do things that we otherwise kind of would not be able to make sense out of. So this is a connection between ideas in a way that this isn't. I mean, this is a connection between different ideas. I mean, dot products are kind of a natural idea too. And there are some situations where this is convenient because it connects an idea to a different idea. And that's nice too. Fully granted. Again, kind of hard to see this coming, but this is the one that ends up being more useful more often. Okay. So again, don't confine your sort of decision-making process to, how do I compute things and which one's easier to compute with? We're only going to be doing a tiny fraction of that in this class. This class is mostly about the ideas. This ends up being the most important idea. Okay. Alrighty. Pause for questions. I'm moving fast. Everybody on board? Okay, so how do you add matrices? And I remind you, we made a decision, I'm going to say a long time ago, but it was last week, of how to add vectors. Right? So like one of the first things we did is talk about how to add vectors. And I urge that we should not just look at the symbols and ask, what would be the most convenient way to write down a formula. That's not a good idea. What you want to do is, if possible, when you can, think about what do the objects that I'm trying to manipulate, what do they actually represent? And how can I make a definition that dovetails nicely with the intuition of what these things are actually representing? Right? So that's what I want to do here. Don't just think about notational convenience. What do matrices represent? What should addition mean in that context? And then let that dictate what it should mean in the context of matrices. So, okay, here we go. What do matrices represent? They represent linear transformations. So I want to ask questions about matrix addition by first asking questions about what should it mean to add functions. Don't forget, linear transformations, they're just functions. They're special kinds of functions, but they're functions. And I claim you all already know what it means to add two functions. This gets used in calculus classes all the time. Right? When you talk about, what's the derivative of a sum of two functions? You're referring to a new function called the sum of the two input functions, and you want to talk about what its derivative is, which means you have to compute its values. And the old, very familiar formula is that if you want to add two functions, the way you compute the value of that sum of two functions is we'll just add the two individual output values. It's you couldn't ask for a more natural sort of answer of what it means to add two functions. We're just going to rip off that. Well, we're going to continue to use that same choice that got made so long ago. Okay. All right. Okay. So, then per my earlier argument, what should it mean to add two matrices? Well, it had better mean a matrix representing the sum of the two corresponding linear transformations, right? So if A is a shorthand representing T, and if B is a shorthand representing S, What should A plus B be? Well, it better be. I mean, it just only makes sense to say that A plus B had, we better choose to define that to be the matrix representing T plus S, for crying out loud. Okay. We already have a definition of what it means to add two functions, and that's going to dictate to us what it should mean to add two matrices. So, okay, so let's compute with that in mind, and here we go. It's a convenient foot in the door to think about columns of matrices, because we know about columns are images of standard basis vectors. That's our definition of a matrix, so it's kind of a nice way to get started. What's the, let's say, the jth column of A plus B, I'm going to ask, just to kind of get the ball rolling. Well, columns are images of standard basis vectors. Definition. Well, let's see here. Now, I've already got a definition of what it means to add two functions. You want to add two functions, well, you just add the output values. That kind of has to be. I don't really have any choice in that. And now, what is this thing? That is an image of a standard basis vector. That's the jth column of A. And likewise, what is this thing? Well, it's an image of a standard basis vector. That is the jth column of B. And so, unavoidably, once you decide that you want to define matrix addition motivated by sort of copycatting addition on linear transformations, the column of the sum is the sum of the individual columns. In other words, an anticlimactic punchline, add matrices exactly the way you wish you could add matrices, just sort of one corresponding elements by corresponding elements. And just like this, if you want to add this matrix plus that matrix, then, well, that plus that goes there, right? And etc. Right? Just you add you add one element at a time. Everybody on board? Now again, if we had been extremely naive about this, if we had just decided to fooey on interpretations, I want the world's easiest, most sort of, the easiest guess of what it should mean to add two matrices, this is what we would have come up with. And that's a terrible reason to make the choice. The reason we use this formula is because we sort of have to, if we want matrices to still, if we want matrices to represent linear transformations, then we're painted into this very convenient corner. Okay. All right. Now I'm going to leave for y'all to think through analogously, what if you multiply a matrix times a scalar? What should it mean to multiply a matrix times a scalar? Well, it better mean whatever it means to multiply a linear transformation by a scalar. And again, that's something that we already know, and go through the argument. And the punchline is that if you want to multiply a matrix times a scalar, you want to multiply this matrix times a scalar, then you just multiply that scalar times all the individual elements. And again, that's probably what you would have guessed if you had just sort of wanted to go into a naive guess. Okay. All right. And now matrix multiplication. This one's a little bit harder to anticipate, but it does work out very nicely, as it turns out. I want to remind y'all of a construction from single variable calculus, and that is the construction of a composition. Y'all remember compositions of functions, I hope? This is the notation that we use. A function composed with another function is it's defined by this formula here. A composition says, first put the input into that function, and then whatever comes out, put that into that function. In other words, it's defined by this. And again, it seems like an unavoidably convenient notation. S of t. Well, the t acts first because it's sitting right there next to the x, right? And then the s acts second because it's, if you will, on the other side. It's further away from the x. Okay. All right, so that's just a flashback. Now, before I go on, I do want to warn you about a landmine that lots of students step on, myself included. When I was younger, I made a huge, I made a teeny tiny error that had huge consequences because I was not being quite careful enough with the point that I'm about to show you. So this is weird, but now notice when we define S composed T, S is on the left, T is on the right. Right? And so look, S is on the left, T is on the right. But if you think about that process, if you think about the functions and how domain and target and what goes in, if you draw sort of the diagram of the composition, S is on the right and T is on the left. Now, what kind of sick and twisted convention made this happen? And there's a couple different ways that you can lay blame. You could say, look, this is unavoidably a consequence of the fact that when we draw functions, the arrow goes to the right. If the arrow goes to the right, then the one that acts first has to be on the left, right? But the way we write functions, the one that acts first, and again, this is how we write functions, the one that acts first has to be on the right. So either the blame goes with we're drawing our arrows to the right, but golly, that's pretty deeply entrenched in our culture, this country anyway. So wow, that's going to be a tough one to change. Or the blame is on the choice to write down functions with the name of the function on the left, and this is where I would actually put the blame myself. Argument could be made that we should not write f of x. Maybe that's a bad idea. Maybe we should write xf. Right? If you think about it, then in some sense, the function whose arrow would otherwise be on the right, well, that function then is on the right, and this seeming inconsistency would disappear. I have been told that there is a small group of mathematicians who insist on writing functions this way for this reason, and I'm so sympathetic, but nobody does this, right? It's just not gonna. It's again, the culture is too deeply ingrained against this. So I think the conclusion I come to and what I suggest is deal with it. Right? I mean, this is, sadly, it's an annoying situation, but the solution is worse than the problem, And so nobody does this, and please don't do it in Math 212. But I just thought y'all would be amused to be aware of that. So anyway, heads up, when you compose, don't forget that the diagram is sort of backwards from the notation. Right. Yeah. So when I was in grad school, I made a mistake in a big calculation that I was doing. In one place, I made a mistake that's morally equivalent to this sort of, incompatibility. This was a calculation. When you're in grad school, you don't do short calculations like you do 10 or 15 different exercises a night, 20 exercises a night, you do one calculation a month, or one calculation, 3 calculations per year, that kind of thing, like really big, important things. So I made this mistake, and didn't discover it for a month, literally. And I had to take a month's worth of work and throw it into the trash can, because it was all wrong. Because I made this mistake here one time, and the consequences were disastrous. So, as you might guess, I don't ever make this mistake anymore, right? I have been through the school of hard knocks on this particular point. So I hope y'all will learn from my bad experience, right? And just be really, really careful on this because it can be, it's a really important, ultimately, mistake to make. Okay. All right. So why are we talking about compositions? Weren't we talking about matrix multiplication? What does this have to do with matrix multiplication? Well, here's the thing. If T is represented by A, therefore if the action of the function T is represented by multiplication by A, and if the action of the function S is represented by multiplication by B, then, this kind of unavoidably has to be that. And let's think about that thing. Man, when it comes time to define matrix multiplication, I sure hope that this associativity property would be true. Now, I guess, we don't have to define matrix multiplication this way, but it'd be a weird kind of algebra if you couldn't use associativity. So here's where I'm going to make my first actual choice, right? The choice that defines matrix multiplication is I'm going to choose for matrix multiplication to be that which makes associativity work. And then unavoidably, right, I have to define this matrix product to be the matrix that represents the composition of the two corresponding linear transformations. So, in the same way that addition of matrices has to correspond to addition of linear transformations, multiplication of matrices has to correspond with composition of linear transformations. And I say has to, in this in this sense of, oh my gosh, I really don't want to not have this. Okay. All right. So that represents that, and that allows us to pretty much, we can just write down again the argument for what it has to be formula wise. Now again, I need some conventions. I've already made the convention that I'm going to use lowercase letters to represent the columns of a matrix. I am also going to establish the convention. I'm going to use capital letters to represent the rows of a matrix. These are pretty, I don't want to say standard, but they're very common conventions. So likewise for B, lowercase for the columns, uppercase for the rows. Right? And now let me just proceed with the idea that, look, a product has to come from composition. So, here it is. Let's look at the columns of this product. Again, columns are a nice foot in the door because they're the images of the standard basis vectors. So, columns are images of standard basis vectors. Product corresponds to composition. That's the choice that we just sort of felt necessary to make. Here's what a composition is. That's not a choice, that's just an observation. Linear transformations are represented by matrices. Again, we've already sort of made that choice. T, the application of T is exercised by the multiplication by A. So we kind of have to do that. And don't forget, columns are images of standard basis vectors. So this, what is T of Ej? Well, it's the jth column of the A matrix. And we now have matrix multiplication actually pretty much narrowed down to kind of one choice. The way you compute the columns of a product is by doing what we've already decided a formula for, namely, we're going to take the left matrix and we're going to matrix multiply by the corresponding column of the right matrix. And we already have a convention for matrix times vector. Matrix times vector is, from a few pages back. Okay, so this is kind of what we're sort of painted into the corner. I'm not exactly unavoidably, but man, pretty hard to avoid. Okay. All Now, what is this formula for matrix times vector? Well, we have 2 points of view on it. The first point of view, my favorite point of view, is that matrix times vector is a linear combination of the columns of the matrix. So we're going to be taking linear combinations of the columns of the left matrix, and we're going to then do that linear combination using the corresponding column of the right matrix as our coefficients. And here it is. Whoops. A column of this matrix product is a linear combination of the columns of B, linear combination of the columns of the left matrix, where I use the corresponding column of the right matrix as coefficients. Again, all that is just a recopy of what that says right there. Okay. Now, we have another point of view that we can use. We have another point of view on what matrix vector product is. Let's think through that one. Right? This is the old high school point of view on matrix times vector. I could take the rows of the left matrix and then dot with the vector. Okay, in other words, dot with the corresponding column of the right matrix. So columns of the left matrix, because that's how matrix vector multiplication works. So columns of the left matrix, and then, sorry, I keep saying it backwards. I'm sorry, I'm looking at the clock. Rows of the left matrix, rows of this, and then dotted with columns of the right matrix. And so again, this is the formula that you probably saw in high school for matrix multiplication. Here it is. An element of the matrix product is a dot product of the corresponding row of the left matrix and the corresponding column of the right matrix. Okay. So now I want to take a quick pause and hit this point real quick. Again, this is what those of you who saw matrix multiplication in high school, they give you this formula and they say, here it is, memorize it. Get good at it. Crank it out. Right? Compute with this formula. Don't ask me why. Right? That's what they told me. Right? So I'm telling you why. The reason that this is the formula is because matrix vector multiplication works as dot products, combined with the fact that I want associativity to be there, combined with the fact that, look, I need for matrices to represent linear transformations. So if you want matrices to represent linear transformations, and if you want reasonable algebra, then unavoidably this old high school formula follows. You just have to have it. Okay. All right. All right, let's see some numerical examples. Here we go. I'm going to get to the third formula in just a moment, but let's compute this matrix product. And this is just arithmetic, but I know that it's helpful to kind of see it in action. So first point of view, we're going to compute the columns one at a time. Let me start with the first column of the product. Where does that first column of the product come from? The first column of the product, well, it's a linear combination of the columns of the left matrix, as we agreed, where I use the first column, the corresponding, in other words, corresponding column of the right matrix as my coefficients. Yeah? Okay. All right. Where does the second column in this product come from? The second second column of the product comes from using the second column as coefficients. I'm still taking a linear combination of the columns of the left matrix, but I'm using different coefficients corresponding to which column I'm computing, different coefficients, and it gives me that second column of the product. So that's the linear combination of columns point of view on matrix multiplication. Now let's do it with dot products. The dot product point of view is corresponding rows dot corresponding columns, right? So the first element is going to be corresponding row dot corresponding column, and that dot product gives us that. This element, top right, we're going to take the top row and the right column, and that dot product gives us that, etc. Computationally, this again, it has an appeal because look, I can do the dot products in my head. I can see the corresponding rows here. I can see the corresponding columns, and I can just kind of look and I can see like, oh yeah, 1 times 7 plus 3 times 8, and bam. So arithmetically, yeah, totally. This is arguably kind of easier, but the importance of linear combinations in understanding linear transformations makes seeing a connection to linear combinations really important. So in the big scheme of things, I think this is the better point of view on matrix multiplication. Okay, and then real quick, I know I'm over time, but here, take a look at this third interpretation. We're not going to do a lot with this in this class, but you can also think about taking linear combinations of the rows of the right matrix using the left matrix for your coefficients. It's algebraically equivalent. Here's the example. You can go through that example on your own, and we're morally done with this section. Okay, so we're done with chapter 3. By the way, let's talk about the exam. So the exam is Monday, right? Time flies in summer terms. We're already at an exam. It's amazing. So the exam's Monday. The fair game material for the exam is everything up through and including what we have done today. So everything through the end of chapter 3 is all fair game for the exam. The homework that is assigned for today, it'll be up through and including chapter 3. All those homework exercises are also due on that same day, Monday. You'll notice on the schedule. Okay, all right. See y'all later. And I have homework.